Today is Thursday, July 9th, and today we will complete this chapter 3. So we will explain how to calculate the diffraction component, which added to the Froh-Dekry-Love will complete the total force exerted by the waves on the ship. Okay? And then I'm going to summarize. There is a group of equations, two differential equations, one for the heave, one for the pitch. They are connected. It's like the whole enemy that we're trying to solve. You will see that it is a system of differential equations which are linear, constant coefficient, second order, and on the right-hand side, you will see that it is a harmonic behavior of the excitation. So the response, eta 3, eta 5, they have to be also harmonic. So we assume that each one of them, eta 3, eta 5, is equal to an amplitude complex times e to the I omega t. Replace it in the differential equations, and you will see that each one of the terms will have e to the I omega t. We cancel that, and we are left only with two unknowns, which are the complex amplitudes for eta 3 and eta 5. So we can calculate that. Excel is quite useful for this, or if you want, you can program, because Fortran, for example, handles quite easily the complex constants, and that's it. After that, we are left only with the explanation of what is the encounter frequency that we mentioned on Tuesday, and then I can give a couple of comments of, for example, what happens when you are not on midship. For example, you are at the bow or on the aft end of the ship. In that case, if you want to determine the vertical motion, you have to combine heave and pitch. Okay, but the problem there is that you have to be careful with the phase shift between those two motions. Also, for example, if you want to calculate the shear force of the ship, okay, then I'm just going to explain how to do it, okay? And we're not going to do that in our calculations. Okay, so that's for today, and that will complete the material for this assignment. So I'm going to share my screen. Thank you. So we're here. So let's just review quickly what we did in the previous session. We said that we're going to follow a very common procedure, which is think that some waves may be very long and some others could be very short, okay? And that allows us to separate the way to calculate the behavior of these waves on the ship in two extremes, and then you will just add these two effects. The first one is that consider that the waves are very long, so they just pass through the object as it were no object at all. That's what we call Froh-Dekry-Love. And the other is what happens if the length is in the same branch of the size of this object. Okay, of course, in this case, these reflected waves will be very important. Also, in the back of this body, there will be a region basically with no waves. So basically here, the crests and the throats are basically gone. Okay, so we recognize that there are these two situations are very different. So when we think that this is the behavior of the ship, we say that we are facing the Froh-Dekry-Love approach. And when we have this, we have to include these effects. We talk about the diffraction problem, okay? This is very simple. This is a little bit more elaborate, okay? And in our case, we are going to calculate this one here, but only for the case of ship receiving the waves from the bow, which is very simple, okay? And in this case, the diffraction potential is not that important, as we would see. Okay, let's go on. So for the flow de Krylov, we said, okay, we have this problem from the gravitational waves. So we have some waves moving, and this is two-directional waves, and this is the Laplace's equation. That means that the fluid is being considered as ideal with constant density. So this is the general expression for the pressure, ds times p, that's differential of force, and n is the normal pointing outwards from the hull. So this n gives you the direction of this force. Since it is acting outwards, we need the force on the ship. That's why we need this negative sign here. If we did component in a vertical direction, we have to get the dot product with the k vector. If we consider only the flow de Krylov, then we're going to apply the Bernoulli's equation, but for the potential function, you see that this is only the incident wave velocity potential, okay? So it's like the waves move, and even though the ship is in here, the waves are so large that they just pass around the ship as there were no ship at all. Basically, that's the idea behind flow de Krylov. Okay, so here, just that, and this is something that we recognize from our previous calculations. So this is the velocity potential, and you see that this is a positive sign, okay? So the waves are moving from the right to the left, okay? So let me see if I can draw here. See, you have the ship is here, okay? And the waves are moving in this direction. That's the situation, okay? So since the waves are moving to the left, that's why we need this positive sign here. It's something that we have to recognize right away. Let me erase, because otherwise I will be, shoot. There, fine. We can go on now. Okay. Okay. We include this into here, simplify omega. We have 2i, so we got a negative here. That's the result. This is a very complex integration. We have to integrate this in the section C, which is at the position X. And then these values here, we're going to integrate them along the ship. So this is a very difficult problem, okay? Very difficult problem to solve mathematically. So some simplifications were included in the, as we will see, okay? And the most important is that instead of considering all of this, the variation of all of this in the section, we take this term here and we replace the z by an average value, okay? It's like a representative draft, okay? And since it is constant for the whole section, we can take that out of this part of the integration. So we take that out, and this is all what we are left, okay? And now we go from the little n to large n, meaning that we're going to calculate this as this were a 2D problem, okay? So it's like having a segment of the ship, a small segment of the ship, and in this small segment, the axial component is neglectable. That's the idea. So we have to do this calculation, and then after we resolve that, we have to integrate all of this along the length of the ship. Here, we do this simplification, and we recognize that dl n3. N3 is the cosine of the theta, which is this angle. Okay, if you multiply these two, you're going to have dy in the negative direction. So if we integrate in the whole section from one side to the other, this integration will provide us with the beam. So that's your beam, which depends on x. So this is an expression to evaluate the Frode-Krylov component. Okay, so we have to evaluate each one of these terms along the length of the ship, and then you just integrate. So this we could have used, for example, first or second rule of integration, Simpson rule of integration, and just obtain a value for this. So we saw that, and we started with the diffraction coefficient. Okay, so the component. So let's consider that there is no velocity of the ship. The ship is fixed. So this is the force, the general expression. In this case, since we are considering only the effect from the wave on the ship is fixed. So if this is fixed, that means that the component of the fluid velocity in contact with the whole surface cannot have component in the normal direction. Okay, if this component were not equal to zero, that means that the fluid will pass through the whole surface, and that's not possible. What else? So in this case, we use again the Bernoulli's equation to replace P by minus rho and the derivative of phi with respect to time. That's why we have the I omega here. In this case, since we have no penetration, in this case, the heave, it's eta 3. We have to be careful. This is eta, this is n, okay? So in this case, we remember this is from the previous problem. In this problem, we have the opposite. The ship is moving, and because of this motion, some waves are getting away from the ship. In this case, in the excitation, the ship is fixed and the waves are reaching the ship. So we saw some similarity. And what people did was, let's try to use the solution of this problem in order to solve the solution of the excitation problem. So this is in here, this is coming from the problem previous. So in this case, the ship was moving, but no waves were incoming to the ship. Okay, so this is already solved. And for this, we have A33 and B33. This is the definition, remember, from the specific fluid, specific velocity potential. And because of this definition, we end up with this expression. People, I had a message saying that my internet connection is unstable. If you cannot listen to me or anything like that, please let me know, okay? So we go on, and then for this, we are trying to relate the excitation with the previous problem in which the ship was moving. Okay, so this is our Gauss theorem. So A here and here, it's a vector function. Okay, so let's suppose that we take the vector function as this one. So phi3, this is a, it's not a vector, it's a, what's the opposite of vector? People help me. Scalar. So phi3 is a scalar, and phi d is also a scalar, but when you see this operator, this converts in a scalar, and a vector. So the result of all of this operation is a vector. So you replace this in here and there, and this is what you have. Then you take something similar for the A and apply again the Gauss theorem. And you see that this term here is 0, and this term here is 0, because you have to satisfy Laplace's equation. So if these two are 0, these two terms are equal, that means that this on the left-hand side has to be equal. And this is what we have. So if we subtract, they have to be the same. So this is equal to 0. Okay? Here, this is the velocity potential to solve the diffraction problem. That's our interest. Phi3, this is a problem that we already have solved. Okay? So this is the previous expression. I just repeat it here. And then because of the non-penetration equation, okay, we can replace this d phi d dn by the negative of d phi I. So in this case, we are satisfying the non-penetration equation, not the condition. There. Now, we are very close. And also, we have this, which is equal to that. Okay, and we can recognize that on this side, we are very close to evaluating the force per unit length on force on the ship because of the diffraction. And that term is equal to this one here. And this is the incident wave, which we know. And this is phi3. And this phi3 is already been solved. So we can express this as a function of something that we know. So this is really clever. It was really clever. Okay, so this is our expression. And we see that we have phi3 and n3, which is this one. So instead of this, we're going to put it like that. There. So in this case, this is already calculated. This is the Frode-Krylov, and this is the one that we're trying to calculate. Phi3 is already calculated. Incident waves are very easy to calculate. So this term here is Frode-Krylov, and this term here is the diffraction. Okay, and this term here, remember that we already deduced an expression that we can apply in order to calculate this Frode-Krylov term. So let's go on with this. I think we end up here last class, right? So this is the diffraction component. Okay, so this is the diffraction there, including the negative sign. Now, we have d phi I dn. So this, by definition, is the normal component of the velocity because of the incident waves. Okay, now we have to recognize that n1 is 0. Why? Because this is a 2D problem. And d phi dy, this 0. Why? Because the wave is a 2D problem. See? Remember that we have the waves in this direction. So we have something like this. This is x, this is z. So in the normal or perpendicular to the plane of the paper, there is no dependence. So there is this component is equal to 0. So if we make this dot product, then the I and the j component will be neglected. And the only one which will be left will be this one times n3. Okay, so let me erase all of this there. We can go on. So d phi di dn, which is in here, is just this times that, And since we are leaving N1, that means that we are applying strip theory, and we are considering that for every section, the axial component N1 is neglectable. And we emphasize that putting the N3 large N, meaning that this is a 2D problem. Now we can replace. Instead of this, we can put this. Okay? And now we can go on, because dphi, dz is something that we know. So here we have z. So we can differentiate this with respect to z. So that will give us a k up here, and the rest will be the same. We have to be very careful because we have a lot of terms here. We replace all of this into here, and this is what we are left with. Okay, so this is the specific velocity potential when we consider the vertical motion. This is wave number. Yeah, this is a constant, e to the kz. This is a term which depends on x, and this is n3. That's n3 depends on the varies in the whole section. So the integration here will take e to the kz and n3. That's a very complex integration. And we do exactly the same as we did before. Instead of integrating this z in the section, we just take a representative value for kz, for z. It's like a equivalent draft. Exactly in the same we did in the Frode-Kirillov process. Okay, so we use for z minus t star, which is a representative draft. And since it is constant for the whole section, we can take it out of that part of the integration. And we are left only with this. Okay? And this is something that we deduced in the previous subchapter. Okay? And that's comes next. So that's exactly equal to minus A33 plus I divided by omega B33. Okay, so all of this is that. That was the main objective of this process, right? Because we could see that because this problem deals with a wave which is reaching the ship, it makes sense to calculate that using this result, which means that the ship is moving and the waves generated are getting away from the ship. Okay, so makes sense that we have these two problems really related. Okay, so this, please be careful. This is little a and little b. That means that this is added mass per unit length. This is a damping coefficient per unit length, okay? So we have all of this, and that will give us the force per unit length. And if we integrate, we get the final force on the hull. So if we replace this in our previous expression, we will have this part here, which is the Frode-Kirillov component, and we have all of this, which is the diffraction component, okay? So we have the whole thing here. In general, the only way to solve this is using, well, there are very special cases, and we will see one of them. But in general, this is something that you cannot do analytically. So what you have to do is, for example, calculate A33, B33, and then you do this operation, and you simply integrate along the length of the ship, and you can apply, for example, one of the numerical integration methods, okay? First or second method of integration. So that's it. So that's the way we're going to do it in this homework.
But one question.
Yeah, sure, go on.
When we solve that equation with numerically, what is the value for x? Because we have to
for this
we have to evaluate in one section of the one section of the chip.
Okay, no problem. I'm gonna try to answer that. Let's suppose that we have this chip. Okay, so this is your x. So what we do is we break this into strips. So we have 8 strips. So for this region, this is the value of x. So you take one section here. Let me draw very large here. So this is more or less the section, okay? So this is the half of the sectional area. This is your B, this is your T. So with BT and the frequency, you can calculate A33 and B33. You also have B, so you can evaluate all of this. Then, if you are considering this position on the chip, then this is the value of X. This is the value of X. Here you have T star. So T star is going to be like a representative value for the T. So T star is usually we take it, let me write it up here, T star. We calculate it with the sectional area and we divide it by B, yes. So it's like an average draft if you want. Okay, so it's up to here. There. So you have this exactly in the way you are doing in this homework. Beam is that. X is the position which define the position along the length of the chip. T star, you calculate it with this, and you have the whole product for this force per unit length.
Okay, thanks, I got it.
No problem, no problem. Then what you have to do is go next. Okay, let's take the new section here. So you have a new value of X. Now the section is not going to be that. It's going to be a little bit thicker, right? Probably it's going to be something like this. And again, you have beam, draft, and you go on and calculate. This is a little bit fatter than this one, so A33 and B33 will be a bit longer. The beam will be this, and you will go on, evaluate all of these terms, and then you apply for the integration in X, you apply Simpson's rule, for example. Okay? Jesus, this is a nice eraser. Okay. After we have all of this, I insist, I'm going to show you my an Excel table when I calculated all of this. Okay, this is for F3, okay? What happens with F5? Let me draw here. So, okay, so let me draw a different color. Let's go blue. Okay, so this is the chip, man. Okay, this is my X, and in the vertical direction, this is Z. Okay, so we're taking a dx, or dx is from here to there. So this is this force, okay, in the Z direction. Wait, I'm sorry, this is F3, pointing upward. The problem is that in this direction, we have the rotation positive, okay? So it's X cross Y and Z positive. But if you have a positive force in the positive X position, that generates a negative moment, okay? So F5, so that's basically the moment to generate a pitch is going to be what? You simply minus the integration of X, and then we have F3, this is force per unit length times dx. And force per unit length is going to be all of this. Okay, you see that the two problems are very well related. See, so you have force per unit length times dx. That will give you this df3 times an arm that give you a moment. But you need this negative because the action of this force will try to rotate in the opposite direction, in the negative direction. Okay, so that's the final expression in this transparency. Okay, so you have an X here and a negative here, and the rest is the same. Okay? When we go back to my notebook, I will go on with the analysis of the units. Questions about this, people? No questions? Okay. There is a very simple, very simple case. Okay? Oh, Jesus Christ. Damn it. Sorry. Okay. This is a very simple case, okay, to show the usefulness of this process, okay? It's a ship which has vertical sides, and the water plane, it's a quadratic polynomial. So the integration is simple to calculate. Okay, that's the example that I'm going to present here, okay? It's very close to the one that you have in your homework. Okay, so in this case, sides are vertical, and here you have that the beam changes like this. So when x is equal to 0, the b is equal to large B. And when x equal L over 2, this is equal to 1, so the beam is 0. Same thing when x equal to minus L over 2. So this is very simple thing. In this case, sectional coefficient is 1, okay, 1, and V over T changes with the same procedure, okay? So this is the Frode-Kirchhoff expression, and you have B, this, and we have to put it in here, okay? The advantage of that is that in this case, okay, the product of this, an exponential function, times n squared, x to the square, you can look it up in an integral table, okay? Or you can remember the chain rule to integrate this, okay? So this is what we did. So since the sides are vertical, the draft of the ship is constant. We have it here. So we put all of this in here, except for the B, which is constant, and we put it up here. So we have to integrate this, and you can look it up in an integral table. That's what I did. This is what I obtained. Okay, so you have to be very careful because the units are kind of complex, right? So this is the expression to evaluate the Frode-Krylov component. It's something very interesting because you have this trigonometric behavior. It's a sinusoidal behavior. You see that KL and cosine KL. That means that remember, these things have like a cycling behavior. That means that for certain values of KL, you can expect to have no excitation, okay? And in other cases, KL will give you a very large value of the excitation, okay? And we will see that in a minute. This is the expression. This is for this very simple geometry. Sides are vertical and water plane is parabolic. This is the expression that we obtain, okay? And here, I took it from, I don't remember what's the reference. But here you have, this is the Frode-Krylov, and this is the diffraction N Frode-Krylov for a parabolic plane. And what you can see here is that the difference is very small. Meaning that in this case, if you calculate the Frode-Krylov, you have a very good approximation of the total force because the difference, which is because to the diffraction, is very small. And this thing here is taken from here. So this is a case when you have the waves coming from the bow. Okay, so the general comment or the general message from this figure is that if you consider the Frode-Krylov component to approximate the total force on a ship in a vertical plane, when the waves are coming from the bow, it is a good approximation. That's the message from here, okay? And now there is also a comparison here. You see here, this is a Series 60. So this is a ship, this is a real ship, okay? And in here, somebody plotted values of this expression. And you see that this is a curve for no velocity. And you see that there is a very good relationship. So it is telling us this is for the force on heave. This is for the moment because of the pitch, non-dimensional way. And it's telling us that to calculate the excitation force, the most important characteristics probably are the length, beam, and draft. Okay, because even though this thing here is taken for a parabolic water plane with vertical sides, the results are very close to those of a real ship. Okay? This is a very nice result. Okay? In the abscissas, you have, there's something I forgot to mention. There are two scales here, right? One is the ratio, L, you can see the L here divided by the length, okay? So, as I said before, see, if you see this is a cyclic function. So, every certain time, the sine of K of L and cosine of K of L tends to cancel. And that's what we see here. See, for certain values, they're basically 0. And then for certain values are 0 and so on. Now, if we go to the left, people, go to the left. That means that in this case here, the frequency is very low. If you have a very low frequency, that means that lambda, that's the wavelength, is very large. okay, very long waves. So if you have a very low frequency, very high lambda, this ratio, A over lambda, is going to be 0, okay? So let me draw here, let me try to say, okay, it's like having, let's see, this is your ship, okay? Let's suppose this is the horizontal, okay? And basically you are having a very long wave, so it's something like this, right? So basically, since the wavelength is so large, basically the slope is on the ship length is neglectable. So it's like having a full effect on the ship with no phase, okay? So that means that you just go up and down, up and down. So in the end, the excitation is simply the amplitude of the wave times the water plane of the ship and times the specific weight. That's for very, very long waves. That's what we see here. Okay, so when we have very low frequency, this force tends to be equal to this product. Rho g, that's a specific weight, Z0, that's the amplitude of the wave, times the water plane area of the ship. That's why we expect this result to close to 1. Okay, and this will represent, and we can say a couple of words about that when we return. I don't know if you have any questions about these things, people. Any questions about this process or details? No? Okay, let's take a break here. And as I said before, please, in the message that I put it in the team platform, I included a survey. Okay, so people, try to complete the survey. It's only 6 questions long. Okay, so it's just to know how can we improve. Okay, so please answer that as complete as you can. Okay, and if you don't feel comfortable writing those comments in English, do it in Spanish. Okay, what we want is to have a feedback so we can improve. Okay, let me say a couple of words before. So I'll try to answer what happens if you try to calculate the added mass for the case of the pitch first. Okay, so we have this situation. This is the origin of our reference system. Midship, positive upwards, and X points to the right. So in this case, Y goes inside the figure. That means that the rotation, positive, goes like that. Okay, so if we consider this little strip, okay, so this strip is located at the position X. So if this strip, if the ship moves with this rotation, that means that this strip will go down an amount equal to X eta 5. So it's very similar to having the ship, having this strip moving in the upward, in the vertical direction. Okay, so if you move downwards, okay, then you can say that this force here, because of this motion, is going to be what? It's going to be A33 times dx, and we have to multiply that by the vertical acceleration. So the vertical acceleration is going to be that differentiated twice. there. Okay? So that's the force because of this rotation. And also you're going to have a term which is also B33 dx, and you multiply that by the vertical velocity. If that is displacement, the vertical velocity is going to be eta 5 dot. Okay? Now, let's go on. If this is the force in that direction, what does that mean? That means that it will generate a moment. So the moment, F5, is going to be equal to what? Only because of this, motion, okay? There's no incoming waves, no nothing, just because of the motion. It's going to be, since it points in this direction, it tries to make it rotate in that direction. So it's going to be minus. Minus what? dF3, this force here, times x, because this is the arm. And we integrate. So let's replace all of this in here, and we are going to have, we have an x here and an x here, right? So we can say that this is A33 x squared dx eta 5 double dot minus the integral B33 x squared dx eta 5 dot. Okay? And then we can say that all of this is the coefficient of proportionality between the moment and the rotational acceleration. So how would you call this? All of this, how would you call this? Somebody. How would you call this? Somebody?
It's A55.
Yes, but what's its name? How would you call this?
Moment.
Exactly. It would be the added moment of inertia. And this thing here, without the sign, is going to be B55. So this is going to be the damping coefficient in pitch. Okay? People, are you with me?
Okay.
Yes.
So you have A33, B33, and you integrate that, you multiply that by x squared, and they integrate it along the length of the ship, and you will have the added moment of inertia. You do the same thing with B33, and you will have, this is the damping and moment for pitch calculations. Okay?
Okay.
So that was one thing. The other thing was what happens with these forces. I was going to present something on this, but I'm going to mention that before we present that in a PowerPoint presentation. We said summation of forces in the vertical direction is equal to mass times the acceleration of the center of gravity. And the center of gravity is equal to eta 3 minus xg eta 5, right? And we start looking at this term here. And we said here we have hydrostatic, hydrodynamics, and also waves. And also we have, remember that we have the volume force there. So all what we are doing is calculating this. So the volume force is just minus W. Hydrostatic is equal to plus V gamma plus, minus APF eta 3 gamma minus moment of times gamma times eta 5. Aerodynamics, we got minus A33, this is large A33, eta 3 acceleration, minus V33 velocity. What else? Minus A35 minus B35. There. And we are calculating this, and this is going to be F3 flow de Krylov plus F3 diffraction. So all of these are on the left-hand side. Okay, in a minute, I will present all of these, but relocated. See, all terms which depend on eta 3 and eta 5, we'll put it on the left. So here we have these two terms, they go to the left. And what are the terms here which do not depend on eta 3 or eta 5? What are those terms? People? What are the terms which do not depend on eta 3 or eta 5?
Excitation.
Mm-hmm. And who is excitation in this case? What is the excitation?
The components of diffraction.
Exactly. This and that. Exactly. So those two will be on one side. Everybody else on the left. And we will go on to solve it. Okay? And the advantage is this term here, both will have e to the I omega t. So we are going to assume, this will cancel that, we're going to assume that eta 3 and eta 5 are equal to an amplitude times e omega t. So everybody will have e omega t. We cancel that term, and the next step is just the solution of an algebraic problem with complex contents, but that's all.
Mm-hmm.
Melendez?
Mm-hmm. That makes a lot of sense. It's
Okay.
because of they are like on the same sub-indice.
Yeah.
And it's confusing.
Yeah, it is. But today I was going to complete that explanation. Okay, now, let me show you, because right now we're trying to see, more or less, you have to calculate this, right? With this explanation, I hope you can calculate these two here. So basically you are able to calculate all of that except this one. So this is flow de Krylov, this is diffraction, and that's where we are right now. Okay, so let's go back and let me show you a piece of this calculation. Here. This is a calculation for the component of the diffraction force. This is a parabolic with vertical sides, okay? And this is what I have done. Since it's a very simple case, I just took 3 sections, and because it's symmetric with respect to midship, that's enough. In your case, I'm asking you to use at least 5 because the variation is harder. So this is what it is. So this is the beam. So in the central part, you have 8.5 and then it decreases. B over T, that's the non-dimensional frequency there. And from this, I take the coefficient C, and with the coefficient C, I can calculate mass per unit area. I'm sorry, mass per unit length, added mass per unit length. Please be careful. This is little a33. Then I go A bar. I have that. And with this A bar, I obtain B33. Now, according to our equation, see, I have these two terms, see? So this term here is real, so that will combine with this one. And this is imaginary. So I can combine these two, and then I can combine as a complex with this one here. So I multiply that by omega squared. I multiply this by omega. So this term here will be combined with, eventually, with the Frode-Krylov. But anyway, right now, it's just the diffraction. So I just integrate by separated by the real part and imaginary part, and these are my results. So that's something that you have to do. And in here, for each one of these lengths, see, I have done this process. So I take these two values and I put it down here. In this case, for example, I'm taking wavelength of 500 meters. So I'm down here. So I take these two values and I copy it down here. And then this is the Frode-Krylov. Okay, this Frode-Krylov, remember that this depends mostly on the beam. And then I have Frode-Krylov. This combines with that. And I have this, which is the real part. This is the imaginary part. And then I can calculate this one. With this one, I can divide it by this term here to make it non-dimensional. This is what I obtain. So this is the process that we have to do. Questions? Questions, people?
I don't have any.
Okay.
We're not there yet.
Yeah, but that's the process. You are right here. You have these values, then that values. And of course, those values are calculated to calculate the added mass, the added mass and the damping coefficient. But little A33 and little B33 are going to be here to calculate the diffraction component. And that's what you have to do. Okay, some people can do this combining directly the real and imaginary and defining a complex. You can do that too, but I prefer not because sometimes this is messy, okay? Because I don't know why, but Excel doesn't limit the number of decimals when you work with a complex. So when you see a number here, you don't see the other part. You don't see the imaginary part because for the real, he uses too many decimals. Okay, that's why I prefer to keep it separated. So you see that each one of these is separated. And only at the end, I just combine with a square root. And that's it. Okay? Okay, so that's what I expect from you. This case is for the vertical, the sides are vertical. In your case, they are not vertical. The sections are circular. But the sectional coefficient and the B over T ratio are constant, which is simpler than this case.
I have to say something.
Yeah.
I want to say something. If we were in the quiz, is correct only to take the real part if you ask us to plot.
No. The problem with this is the following. No, you can't forget the imaginary. The problem is here. that if you take the real part of this, okay, the problem is that you are multiplying by cosine and of kx and sine kx. Can you see my screen now?
Yes.
The PowerPoint? Okay, let's remember this. Let's remember. See, this is real. This is a I'm sorry, let me work with the force, not with the moment. Okay, let me work with the force. So this is real. This is real. This has imaginary and real. This is real and this is imaginary, right? So let's call this just R, and let's call this I and little I. So, but here you have C, that's cosine, plus I sine, right? So if you multiply the two, then you can take the real part. And the real part is going to be the cosine of kx times this, what we call R, minus the sine of kx times the imaginary part. This is the real part. Okay? Miranda?
Right.
Yeah. Okay. Okay, so don't forget about this one here. And I hope I hope I include it in my case. Let me, oh shoot. Let me, okay, let's erase that. It's taking J11 times 11, yeah. I guess I'm taking it because here, yeah, here you have the cosine of K8, C8, yeah, that's a K. So you're taking, this is the cosine of Kx. So you are considering the component. And here you have the, yes. Yeah, but that's what you have to do. Okay, people? And this is very nice because the blue is the flow de Krylov, and the, I don't know what color is this, the orange is the combination of the flow de Krylov and the diffraction. And you see that the influence of the diffraction in general is small, in general. But it's a good idea to include it if we can. Okay?
Okay. In the assignment, in the same homework, you ask also to plot the chip profile in the time.
Okay.
What do you mean with that?
Let's do this. Let's do this. Okay. Oh, here. Okay, we can review that on next Tuesday, but that's where we are heading, okay? And I think this is what Melendez was asking. Okay, here we have rewritten, and we have located all the terms which depend on eta 5 or eta 3 on the left. This is the equation for the heave, this is the equation for the pitch. And those terms which do not depend on the eta 3 or eta 5, we put it on to the right. Now, eta 3, F3, and F5, these are the wave forces, which we have just explained how to calculate. Okay? What do we do next? We assume that the solution is equal to eta 3, this is a complex constant, times e to the I omega t. These two forces, F3 and F5, they are also dependent on E I omega t. So after we do this replacement in here, each one of these terms have this term here. So we cancel. Now, if we assume that this derivative is going to be minus omega squared times that, this first derivative is going to be I omega zeta 3 times that. So all of this can be calculated. And this is the way we replace it. So all of these are constant times zeta 3 times that. All of these are multiplied by zeta 5, these multiplied by zeta c, this multiplied by zeta 3, and that's it. So you see that all of these terms have this common term. So we can cancel. And after we do that, we are left with a very nice system of equations. So D11 is going to be everything which is multiplied by zeta 3. So it's this. D12 is multiplied by zeta 5. So it's all of this, etc. F3, F5 are the amplitudes of the forces except e to the I omega t. See, this bar here means that each one of these terms are complex. After you have all of these, remember, D11, D12, D21, D22 are completely calculated. The problem is that you have to be careful because they are complex. Because this part here is real, you have here clearly, this is the imaginary. Imaginary, imaginary, imaginary. So you have to evaluate them very careful because we have real, this and this is real, and this is imaginary. But after you have this, you can solve for zeta 3 and zeta 5. This is the amplitudes. Okay? So you can go up to here. And then I can try to explain how can we draw this profile that I was mentioning. Okay? People, please.
Okay.
So,
Okay.
in this equation, you have already A33, B33. This is easy. In your calculations, these terms are linking, and eta 3 and eta 5 will have a very decent value, you will see. You have, I explained this. This is the added inertia. This is the pitch damping. This is inertia. You can calculate that. We're explaining today how to calculate this, which has two parts. Okay, let me go back. Here. So you see that you have all of this, and you are having e to the I omega t. So all of this is like the amplitude of the flow of the Kirillov. In this case, this amplitude is real. So you have to add that to the amplitude of the diffraction part. So this, all of this in blue, this is the amplitude times e to the I omega t. And that's why here, this term here, we write it as this. So all the terms that I surrounded in blue is this one. And we left out e to the I omega t. If we recognize that this is a real system of equations with constant coefficients, and on the right-hand side you have this term here, then the solution has to have the same form. When you replace this into here, you see that each one of these terms has the common e to the I omega t. And then you proceed, cancel that, and you can solve this. So you can find the amplitudes of the response. Okay, if there's no more, okay, if there are no more questions, then I'll see you Monday, and you tell me the time. Okay?
Okay.
Bye-bye now.
Thank you. Have a
You're
good
welcome.
day.